well, because you're going to see some of the trig identities today, and those always show up on the ACTs. So you're definitely getting some big pieces here. They're going to help you with those. And I also realize some of the seniors are probably having to take the ACTs because you didn't get the ACT last spring like everybody else did, so you're probably having to pay for it and do that. So this is definitely going to be benefiting everybody here. The other change that I have to make is late homework. And that's because I feel like my policy of giving full credit up to this point has been enabling some people to not turn things in on time. And the syllabus does say that all homework will be due the next day. And so from now on, when an assignment is turned in when it's supposed to be, you get the 2. If it's late, you get a 1. And that's because, like I said, I really fought with myself a lot about this last night. I feel like I'm enabling some people to fall behind and stay behind. And that's going to affect your grade, and I'm not going to be responsible for helping you out with that. So make sure that you're doing those assignments each and every day and that you're submitting those. So back to the way it would have been had this been a normal school year is what we're going to do. Alrighty, so we've got some biggies here in Chapter 5 and Section 5.1. And from Section 5.1 we have, I can identify and work with trigonometric identities. Sure, once I tell you what they are and we talk about how to use those and reason with them, you're going to go, oh my gosh, this is a piece of cake. No wonder they put this on the ACTs. And all they're doing is they're really checking to see, are you in a class that other juniors are not in when you're taking the ACTs, so that you understand this. I can simplify trigonometric expressions using basic trigonometric identities, Pythagorean identities, cofunction identities, and odd-even identities. And we're going to talk about all of those today. We might not necessarily... We do an example of every single one of those today. We get through those. I can solve trigonometric equations using trigonometric identities and properties of algebra. That's going to have to wait. So tomorrow you'll have a video lesson on 5.1 day 2, and then Monday we'll finish up 5.1. There's a lot here. It's all good stuff, and it is not necessarily difficult. It's just that it's the first time that you're seeing it. So you need to get to work. There's all the things we're going to do. And everything that we do is linked back to our understanding of the unit circle. So how we're going to start today is I'm just going to give you some time here to think about, what are these? Can I find them? And there's 10 of them. So I'll stop the recording and I'll just give you a chance to go back to, okay, how did I do this again? We took a speed test on this at one point. Do you remember that? Yeah, so try and remember those strategies that helped you do this, well, effectively, but quicker. I realize not everyone is done. There are 4 or 5 people in here that have completed these. What this is about, again, is me seeing the strategies that you're still using. I'm with those of you, every time that I took my college trig test where we had this, I drew my 30, 60, 90 and my 45, 45, 90. I'm a visual learner. That was easiest for me. If I drew those, I wasn't going to get anything wrong when I went through that. Some of you are now saying, you know what, I'm just going to use the denominator. Because if it's a 4 down there, that's a 45-degree angle, and if it's a 3, that's a 60-degree, and if it's a 6, that's a 30-degree, and I'm just going to quickly figure out which quadrant it's in to know is it positive or negative, and then I'll do it that way. And some of you are using a mixture of the two. I see people that are, like drawing things with their hands. That's perfectly fine. Whatever helps you get there is what you need to do. And I do want to put them up here so you can check them. And if you didn't finish, you can just, if it bugs you that it's not done, you could finish those a little bit later. But we have 0 and 0. Oh, there was another strategy I wanted to mention. It looked like somebody had gone through and done all the quadrantal angles first before they started all the other ones that would require an actual triangle to take a peek at. So lots of strategies out there that people are using. And this one is square root of 3 over 3. Cotangent of 7 pi over 4 is negative 1. And then we have negative 2 square roots of 3 over 3. 6 is negative 2 square roots of 3 over 3. Cotangent of 4 pi over 3 square root of 3 over 3. Secant of pi, -1. And the last two are -1/2. So, what this was really about was finding strategies that work for you. Because that's really important when we start talking about the identities. Because identities are things we have to know. It's not a, oh gosh, I'll just remember this for the homework and then I'll be done with it. Identities are things we have to know. So whatever way you can get your brain to wrap itself around these identities and hang on to it, that's what you want to do. And I'm going to be talking about some of those strategies today as we look at our identities. So we have fundamental identities. Yeah, the basis for what we're doing in trig. And as we look at this, I hope some of this is kind of a duh moment for you where you go, well, yeah. So the symbol equals. It does mean several things. I mean, it does say equality of numbers. We all know 1 + 1 is in fact 2, and 2 does equal 2. So if they're equal, their numerical value is the same, it's a true sentence, that's equality of numbers. But we also use it to show equivalent expressions, things that because of our background, because of the properties that we know of algebra, 2 times the quantity x minus 3 equals 2x minus 6. Somebody in the first grade is not going to have a clue that those are in fact equivalent. They would look at that and say, but this isn't the same as this. But once you learn some algebra and you learn how to distribute, you know those are equivalent. They're not equals because they don't say exactly the same thing, but they're equivalent, and that's what the equals is saying. It's providing a true sentence. This one is an open sentence. Might be true if we find the correct answers. Might not be if we don't find the correct answers. So it could be true or false depending on whether x actually is a solution to the equation. And we've learned we'd subtract 3 from both sides, take the square root, and go from there. This is an identity. And identities are things that are always supposed to work. They will always happen. And this identity is called the Pythagorean. Actually, when I think of the Pythagorean identities, this is the one I think of. There are 3, but this is the one I think of. And usually, books will write it sine squared t plus cosine squared t equals 1. When we talk about trig, this is one of the shorthand ways of writing that we want the cosine of t squared, the sine of t squared, without the parentheses. So we shorten that up. And every other trig book I've ever seen, and I've seen a lot of them, starts with sine first, because we learned those, sine, cosine, and tangent. So most books say, let's stick with that. Let's do sine first and then cosine. It doesn't matter which one you put first. They're going to be equivalent. So we can do that. Equations that equate 2 expressions that are true for all values in the domain of both expressions. So there's the biggie. We know that sometimes sine and cosine could come out to be something that might work out undefined. We've seen situations like that before. Usually with the secondary trig functions that happens. So we're saying, yes, this is absolutely an identity. It will always be true, but there are some situations where things go a little wacko. So domain of validity is what we need to take a look at. And that's values of the variable for which both sides of the identity equation happen to be defined. So we know goofy stuff happens with the quadrantal angles. We were able to find all kinds of things, but the quadrantals, that just messed things up. So we have basic trig identities, which we already know. We know that cosecant is the reciprocal of sine. We know that. We know that secant is the reciprocal of cosine. We know that cotangent is the reciprocal of tangent. So when we take a look at these should make total sense. They're things that we already know. These, remember I had warned you, this is a biggie. And first-year trig students sometimes have trouble with that one because it just doesn't seem to stick as well as the others. But we have to remember that tangent is sine divided by cosine. And then it makes it really easy to remember, yeah, cotangent, you flip that, cosine to sine. So tangent is sine over cosine. Now this exploration says we're going to show you domain of validity by showing you that sometimes you can't find some of these, even though they're identities and they're always supposed to work. There might be a number that's not in the domain of validity. And the first one says we're going to consider theta, our angle, to be 0 radians. And I get this picture in my noggin right away. So there's our unit circle, and there's little 1, 0 out there. And I remember that this is cosine, the x-coordinate. And the y-coordinate is sine. So I started thinking, well, that will mean anything up there that has sine in the denominator is going to be undefined, because then we're going to be dividing by 0. And that's what they want us to get at here. It says theta equals 0 is in the domain of validity for 3 of those up there. For 3 of them, we'll get things like 1 equals 1, 0 equals 0, etc. For 2 of these, one side will be defined and the other side won't. We'll be able to get a number on one side, but the other side will be undefined. And then the third one says for 3 of these identities, both sides are going to be undefined. We won't be able to find them. And that's because 0 is not in their domain of validity. So let me show you what they're getting at. Cosecant. Cosecant of theta. When we're using coordinate trig, you have to go back in your head and remember sine was y over r, cosine was x over r, and tangent was y over x. So when I think about cosecant, I think, well, that's what you get when you flip sine, so that's going to be r over y. Well, r is the radius of our little unit circle, which is 1. My equals in the wrong spot there. So r over y would be 1 over 0. Hey, that's undefined. So this side is undefined. And 1 over the sine of theta, well, sine of theta is 0. So 1 divided by 0, this side is going to be undefined as well. So now I think about secant. Secant is cosine upside down, and cosine is x over r, so it's going to be r over x. 1 over 1. That's a 1. Cosine of theta is 1. 1 divided by 1 is 1. Hey, that one works. We get a number value on both sides. I'd like you to go through the other 1, 2, 3, 4, 5, 6 of them. Put your u's for undefined, zeros and ones on each side of those, and then we'll come back together and answer their questions. When you're done, you can take a peek up there and see if you have the same thing. If something doesn't match what you have, take a couple of seconds here to look at it again, and if you need me to explain why one of these is the way that they are, please let me know. Remember, that undefined piece always comes from having to divide by 0. So let's answer their questions. Number 1 says theta is 0. It's in the domain of validity. It absolutely works for 3 of these basic identities. We get the same thing on both sides. It's an actual number. 0 equals 0, 1 equals 1. Well, not this one, but secant. Secant of theta equals 1 over the cosine of theta. That one's good. It's the only one in that row. We go down to the next row, and we see the middle one is the cosine, and it's reciprocal of 1 over the secant of theta. And then we get down to the quotient identities, and we see tangent as sine over cosine. Works for 0. I mean, this is specific. We're just talking about radians, 0 radians at this point. And then 2 says for 2 of these, one side is defined, but the other isn't. So we were able to get a numerical answer for one and a u on the other. And that ended up happening with sine being written as the reciprocal of cosecant. Tangent being written as the reciprocal of cotangent. Not in the domain of validity. And that's what we see in number 3 as well. For exactly 3 of the basic identities, both sides of the equation are undefined at theta equals 0. Which 3 are we talking about? Well, in this case, they did both end up undefined. So they do work. It just feels like they don't work because we have to put undefined. So cosecant of theta is 1 over the sine of theta. Cotangent of theta is 1 over the tangent of theta. And where's our other UU? The very last one. Cotangent of theta equals cosine of theta over sine of theta. So, can it truly be called an identity? Yes, it can. But we have to remember that quadrantal angles mess with some of these. Works for everything else, but the quadrantals, we're going to have to be careful and see whether or not what we're doing actually is in the domain of validity for what we have, because that involves zeros when you're talking about the quadrantal angles. Well, like I said, I don't think anybody was shocked at this list. I mean, there's nothing here that we haven't already talked about. And it just gave us the fancy name for them, but we know these are reciprocals, the reciprocal identities. These quotient identities, yeah, they usually take a little bit more getting used to. So now, here come the biggies, the ones you're going to see on the ACTs, because they want to see just how far did you get in trig. And the first one is cosine squared plus sine squared equals 1. Again, lots of textbooks use sine squared theta plus cosine squared theta equals 1. And I'm not going to be able to help it. That's just, you know, I've studied from so many trig textbooks, and overwhelmingly they do that because they want us to remember sine, cosine, tangent in that order. So this, we already saw where that came from. We went through the process of doing this when we were right at the beginning of trig. Because we said, if you're going to talk about coordinate trig, your x's are always cosine and your y's are always sine. And since that's a right triangle, it'll be cosine squared plus sine squared equals r squared, which is 1 in the unit circle. So I feel like, hey, I already know that one. That's just a squared plus b squared equals c squared. The other two. Okay, Cedarholm, do we have to memorize those? Not memorize, but know. Yes, you have to know them. But here's what you're going to do. You're going to start with this one, because we all know this one. Sine squared plus cosine squared equals 1. And you're going to very quickly develop the other two. Here's how you're going to do it. You're going to take cosine of t squared plus sine of t squared, or sine t squared plus cosine squared equals 1. And you're going to divide every single term there by cosine t squared. So let's take every term and divide it by the cosine of t squared. Cosine of t squared divided by cosine of t squared, that's a big 1. Sine of t squared divided by cosine of t squared. Oh, that's that one Cedarholm said we got to hang on to. That's tangent. So that's tangent of t squared. 1 over the cosine of t squared. Let's see, the reciprocal of cosine. That's secant. So that's going to be secant of t squared. 1 plus tangent of t squared equals secant of t squared. Wait a second. It's that one. Yep. So if you go through and mentally divide them all by cosine squared, you'll get the second Pythagorean identity. Now let's go back through it, go back to the original, but this time we're going to divide everything by the sine of t squared. Cosine squared over sine squared. Hey, that's cotangent squared. Sine of t squared divided by sine of t squared, that's 1. Reciprocal of sine. Hey, that's cosecant. Cotangent squared plus 1 equals cosecant squared. Oh, look at that. That's the third one. Now, you probably won't be able to help it. We'll be working with these so much, you're going to memorize the other two. But if you don't, this is a great way to get them, to just develop them really quickly. Some people look at these and say, oh, I can do this, Cedarholm, because I see both of these have the cos, and these don't. So tangent and secant don't have the co, but cotangent and cosecant do. I would prefer that you think about them this way. Here's why. You will never forget them because you can always find them in a matter of seconds. You'll remember sine squared plus cosine squared equals 1, and you'll get the other two in the matter of seconds. What I don't like is the idea that 10 years from now, if I encountered you on the street and said, what's the Pythagorean identity, that you'd go, oh, I don't know. I want to have a way that you can find these without having to memorize everything. So this says let's use them. And that's going to be the goal of the homework for this section, is using the identities. Find the sine of theta and the cosine of theta if the tangent of theta is 5 and the cosine of theta is greater than 0. Now, they went to great pains to get me to think about what quadrant this is in. And I know that because they told me tangent is a positive 5, and then they mentioned that the cosine also has to be greater than 0. It has to be positive. So it's got to be first quadrant. Right there. And I need to use an identity that uses tangent because they gave me that one. So I flip back up here. And I see, there it is. 1 plus tangent squared theta equals secant squared theta. Well, I'll start with that. Now they told me tangent is 5, so I'm just going to substitute that in there. Follow the order of operations and do a little math. 5 squared is 25. 25 plus 1 is 26. Okay, well then I have to take the square root of both sides, and that would mean doing the plus or minus thing. So if I hadn't already started to think about the quadrants, hopefully at this point I'd go, oh yeah, I got to know what quadrant this is in. But I know it's in the first quadrant, so I need the positive square root of 26. Now, they didn't ask me to find secant. They asked me to find sine and cosine. But secant, isn't that one of those flipped? Which one do you flip? Oh, so if I just flip this and make it 1 over the square root of 26, I'll have the cosine of theta. And of course, we'd know we have to rationalize the denominator by multiplying by the square root of 26 over the square root of 26, so we can get this perfect. As the cosine of theta. Well, I have a cosine, but they also wanted me to find sine. So what I want to do is think, how could I get that with all the identities? Pretty obviously, I could use sine squared theta plus cosine squared theta equals 1, but there's an easier one and a faster one, and that's using tangent as sine of theta over cosine of theta. And because we have to get used to that one, that's the one I want you to write down, because it makes the math a lot easier with many of these. Because we know what tangent is, they gave us that. It's 5. And we just found the cosine of theta. We said it was the square root of 26 over 26. And I could either just multiply both sides by the square root of 26 over 26, or I could plop a 1 underneath the 5 and cross multiply, because that would make it a proportion. However it gets you there the fastest, that's what you want to do. And again, positive, because we're in first quadrant. But the big deal is use of the identities. You know, using the identities that we have to make this easier. If somebody were to, and this is going to happen on the test, somebody's going to draw me a triangle, they're going to use the Pythagorean theorem, they're going to label this out. You can't do that when it says use the identities. You have to use those formulas. So don't fall back. I know we want to because we were really good at that, but don't fall back on those old patterns. Use the identities. So now, we're not done with identities. On this page, we see the cofunction identities, and we had talked about this. Co in geometry means complementary. It means they add to 90 degrees. So when we were talking about angles A and B and finding basic trig ratios of those, we noticed some stuff. We noticed that if you find the sine of A, that's going to be exactly the same thing as the cosine of B. Because they're complementary, because those two angles add to 90 degrees. And the cosine of A will give you the same thing as the sine of B, because they're cofunctions. That's how it works. Tangent, come on, Blue, there we go. Tangent of A is the same thing as the cotangent of B. And then secant and cosecant. Cofunctions. Sine and cosine. Tangent and cotangent. Secant and cosecant. They are cofunctions of each other. That's actually how they got their names. So being complementary. Now, being complementary helps us find things. For instance, if we get the sine of A, we would immediately be able to tell them, hey, that's the same thing as the cosine of B. And that's what these cofunction identities are saying. They're saying because this is 90 degrees, that means there's 90 degrees left for the other two angles combined. So if we take 90 degrees and subtract whatever one angle is, we'll get the other one. And it's not written with 90 degrees, it's written in radians so that it's exact. So notice all of these have sine of pi over 2 minus theta, tangent pi over 2 minus theta, secant pi over 2 minus theta. To remind us, it's because they add to 90 degrees, and 90 degrees minus theta will give you the other angle, that this whole thing works. So we have to remember that. Sine and cosine, tangent and cotangent, secant and cosecant. Because here's what the book's going to do. They're going to write this as theta minus pi over 2, and they're going to hope they catch you. The 90 degrees comes first. Pi over 2 minus the angle. In fact, our first example we're going to do on this, they try to pull that trick. So don't let them do that. Now, odd and even functions. We've just gotten done graphing all of these. And hopefully, because I haven't gotten to start your test yet, because Algebra 2 had their tests the day before you. Hopefully, from what I was seeing beforehand, those graphs are going to look fantastic. But this comes down to, where does the negative make a difference, you know? And the negative makes a difference with sine because it's odd. But what we said was, instead of leaving it here with the x, we're going to put it out in front because then it's just easier to work with. So same thing with its reciprocal, cosecant. The nice one was cosine and its reciprocal because it's already even. The negative doesn't need to be there. We can drop it. Again, tangent and cotangent, those were odd. And so those we have to keep the negative. We can just relocate it and make it easier on ourselves. So example 2 says we've got some more identities now. Let's see what we can do with them. And like I said, look what they did. They're thinking, you're new to this. You're not going to catch that. Yeah, we're going to catch it. So we would have to factor out a negative to make that look the way that it's supposed to look. And normally I wouldn't put the -1 there, but I want people to look at the notes and see, hey, that's what we did. We really factored out a -1. And then we have to decide if we can lose the negative or if we just move it. Do we lose it for sign or do we move it? We got to move it, so let's put it in front. Hey, wait a second. I think this was one of those co-identities that we had up there. Let's see. Sine pi minus 2. Oh, that was cosine. So this we could substitute cosine of theta for, because the whole thing was one of our cofunction identities up there. Okay, so if I need the sine of theta minus pi over 2, it's just going to be the negative of the cosine. Wait a minute, didn't they tell me what the cosine was? They did. So by using the identities, we can find it. Cofunction identities. B says, using identities, simplify this. It's going to come out to either 1 or -1. They already gave us a 50-50 chance. And it says we're going to take the sine of x times cosecant of -x. And the first thing I'm thinking is, well, why did they put cosecant up there? That's a secondary trig function. I think they're trying to mess with me here. Cosecant, what do you flip to get cosecant? Sine. All right, so I can see what's going to happen here. I better put my equals to break up my work here. But I got a little negative to take care of. With sine, can you just lose the negative, or do you need to move it? Okay, so we can put it wherever we want to over there. I think I'm going to put it up there with 1 on the top. Oops. Too many equals. We move it. Well, sine of x is going to cancel out. It's -1. And there it is. So obviously this one was to get us thinking about the cofunction identities, and this one was to get us thinking about just regular reciprocals, you know, and what's going to happen with those. But we've got a lot more to go. So we turn the page. And like I mentioned before, I took a college trig course, and whenever I knew the identities were going to be on there, here's how I started the page that had anything to do with identities. That was my start. I write that at the top. Then, in my head, visually, I'd go through and divide everything by cosine. So sine divided by cosine, that would be tangent squared theta. Cosine divided by cosine, or cosine squared divided by cosine squared, is 1. 1 divided by cosine squared, that's going to be secant squared theta. And I had the second Pythagorean identity. Then I'd quickly go back and say, all right, now it's sine squared's time. Let me divide everything by sine squared theta. That'll be a 1. Cosine squared over sine squared, that's cotangent squared. And 1 divided by sine squared is cosecant squared. And it would be right at the top of the page, and I could use that for anything that involved the identities. So this says, simplifying by factoring and using identities. Simplify the following trig expressions to a power of a single trig function. Cedarholm, how would I know that this is the page I should write those down on? Powers. Anytime you start seeing powers of the trig functions, you should think, ooh, I got squareds coming out my ears in those formulas. I should be using those. But A is a cube. Well, if I could figure out a way to get that down to a squared, I think things would go nicely. Oh, that'd be factoring. I should factor out sine of x. Well, let's see what happens. So if I take 1 sine of x, that'll leave me with sine squared x plus cosine squared x. Hey, wait a minute. What's sine squared x plus cosine squared x? 1. And I have it to a power of a single trig function. Simplified. I look at b. I don't see the powers. And I know all the powers in my trig identities have to do with squaring. Well, maybe if I FOIL this, I'll see what I need. Secant squared of x. Oh, I don't even have to do the O and the I. It has a sum and difference pattern. I can just go straight to last times last. Oh, I think I know that one. Let's see. Secant, subtract a 1. That would be tangent squared theta. Tangent squared x. There it is. C is messy. Do you agree? They're hiding stuff. How do I know they're hiding stuff? Well, all of a sudden, instead of writing secant, they're writing 1 over cosine. They're hiding stuff. So, let's figure out what those are. So 1 over cosine is secant theta minus 1. And then, I'm not going to be able to fit that on the same line because I write too big. Cosine squared theta plus, I'm going to leave it secant negative theta for just a minute, plus 1 over cosecant squared, sorry. What would that be? If you flip cosecant, you get sine. Now let's see what we can simplify that back part to. Do you see your powers? Secant. What do we flip to get secant? Cosine. Is cosine even? If it's even, do we need the negative? Ooh, excellent. Because this is 1. Deja vu! Didn't we just solve that? And there it is. So using the knowledge of, hey, Pythagorean identities have lots of squareds in them. So if I can see things that are squared, then good things will happen. Seems to be a theme with these problems, isn't there? So with this one, we obviously would FOIL these two. Use our equals to break it up. Hey, that's exactly what we had last time. That's tangent. And now when you get to this point, one of the major tips that you can tell trig students is write everything in terms of cosine and sine, and good things will happen. So we look at tangent squared and we say that is going to be sine squared over cosine squared. But we don't divide fractions. We multiply by the reciprocal. Hey, sine squared is going to cancel out. We want a single trig function. 1 over cosine. What's that? Secant. This is secant squared x. Notice how, because I had more space, I was able to go horizontal with this one instead of going vertical. And the equals break it up. So totally easy for anybody that's looking at it to figure out this is the step I went to and go from there, showing that equivalence that we talked about. And that was where I got with first hour, even with my computer crashing on me. So that blue one up there will be the assignment that's due tomorrow. Because again, everybody knows you should be doing your homework the night that you've learned something. It's best to learn math in chunks, little digestible bits for your brain, a little bit each day. And it's not one student or two students. As I looked at my 2 hours of pre-calculus, there were probably about 10 people that have started to get into that bad habit of letting homework sit.